In this video we're going to move on from polyesters and have a look at polyamides. So polyamides are repeating amide groups, and again from your carboxylic acids study you should remember about amides and how to form an amide. So amides themselves come from the reaction of amines with carboxylic acids or with acyl chlorides. So polyamides, similar to polyesters, are going to come from the reaction of a dicarboxylic acid. So again, we want it to repeat over and over again. We need it to be on both sides. Dicarboxylic acid and a diamine. So two amine groups. Again, we're going to eliminate a small molecule, and in this case again it's going to be water. The OH from the Q group, exactly the same as in polyesters, and the H this time from the amine rather than the alcohol. So very, very similar to polyesters. Just watch out, there is still going to be one hydrogen left on the nitrogen, because an alcohol group only has one hydrogen, but an amine, primary amine group has two. So there will still be a hydrogen left. And we can look, we formed, again similar to our last little video, we formed our amide functional group. Now remember that an amine is an N joined to carbon chains, but an amide is an N joined to a carbon chain and joined to a C double bond O. So amide joined to a C double bond O. Amine just on a carbon chain. Similar when you think about alcohol, it's an OH group joined to a carbon chain, but put that OH group on a C double bond O and it suddenly becomes a carboxylic acid. It gets a different name. We've got an amide functional group and we've got an amide bond or amide link. This is our amide bond or amide link, and again we've got amide bonds or links at the ends, our trailing bonds as well. So they go off to the next one. Now those of you that are studying biology alongside chemistry might look at that group and think, hang on a minute, that's a peptide bond. And I can understand why you would say that. It looks very similar to a peptide bond. It is only a peptide bond if that link is joining two amino acid groups. So if it's joining chemicals that aren't amino acids, in this case these aren't amino acids, then it's an amide bond. When it joins amino acids, it's called a peptide, and we will come and look at those later. This bond is called an amide link. So when this link forms, we lost that bit that we highlighted back up there, that little bit of water. Okay, so we were removing, again, the OH from the Q, and we're removing a hydrogen atom from the NH2, the amine part of the amine. Like we mentioned in polyesters, there are a couple of these polymers, condensation polymers, that are on AQA specification that are named in the specification, and nylon 66 is another. Now the name nylon 66 is in relation to the carbons in the chain. So the first number refers to the amine and the second number refers to the carboxylic acid. So what this tells a chemist is that this is a polyamide, nylon, made with an amine that has 6 carbons and a carboxylic acid that has 6 carbons. So we've got an amine with 6 carbons, hexane, and the amines are at either end, so 1,6-diaminohexane, and then we've got a carboxylic acid with 6 carbons, which would be hexane as well. So the carboxylic acid is the second number and the amine is the first number. So if I said nylon 610, I'd be looking at the same amine but a bigger carboxylic acid with 10 carbons. I used to think of this as just being in alphabetical order, amine and then carboxylic acid, the numbers were in alphabetical order. So we're going to try to draw out the monomers, so I'm going to pause the video, see if you can draw out 2 hexane chains and start to put an amine group on one end of one of them and a carboxylic acid group on the one end of each of the others. So there you go. There's a couple of things you might notice that might look a bit different on my structures than on yours. A couple of choices that I've made. One of the choices I've made is there was a lot to draw out there, so I've grouped together the CH2s that form the hexane chain and said that there are just 6 of them repeating in 1,6-diaminohexane. So I've written CH2 bracket 6, that saved me a bit of time. I've also drawn out the amine groups and you'll see why in a second. And then on the carboxylic acids, again, I've grouped the CH2s, but just be careful. So although there are 6 carbons in the chain, 2 of them are in the Cu group, so there's only 4 in that bracket in the middle. And this is a common multiple choice question, just to catch you out, see if you really understand, because you might look at it and go, oh, there's 4 there, so it's a 6 and a 4. But actually, there's 6 carbons in each of these monomers, so it's a 6 and a 6. Now I'm going to highlight the bits that we lose. So remember what we've said, we lose the OH from the Cu group, and then we lose a H from the amine, and that is why I drew my NH2 out, so that I could highlight one of the hydrogens and not both. Which is why NH2, it's a bit trickier. And then I'm going to join those 2 bits together to make a polymer. So in I go. I'm going to start with the top one. I've got my trailing bond to an N that's got a H. It doesn't matter whether that H points up or down. Then I've got 6 CH2s, and then I've got another N with a H. And then I've got C with a, joining it to my carboxylic acid, so C with a double bond O. And I've got CH2 brackets, this time 4 times, and a C double bond O, and then my trailing bond. Remember that we've got our amide bond now is between our C double bond O and our N. So that's that amide bond there. And the trailing bonds are also amide bonds, so if you wanted to label them all, these would all be amide bonds. So that's our structure. Now, nylon 6,6 is a very, very strong material, so it's used in lots of things. It's very resistant to abrasion, so it's used in lots of clothing, and carpets, ropes. It's very, very strong. Parachutes, these are the sorts of things that we might use it in. But there's some of the uses there. That's just to give you an idea. Very unlikely to get asked questions about the uses of a specific polymer. Okay. So we're going to move on. We're going to have a look at Kevlar now. Some of you might have heard of Kevlar. Kevlar again is mentioned in AQA specification by name. Kevlar is what you'll find in bulletproof vests. Fire officers also wear it in their fire retardant clothing. So pause the video and have a go at drawing out 1,4-diaminobenzene and benzene 1,4-dicarboxylic acid. So there you go, I've drawn out those 2 monomers. Well, a bit wonky, but they're there. And you can see that we're going to remember to lose the OH from our carboxylic acid and the H from our diamine, and we're going to squish those 2 together. It doesn't matter which one you draw first. I'm going to draw the carboxylic acid first this time, so I'm going to go in, losing the OH, so my trailing bond goes to the C double bond O, get my hexagon in there, and again I've got another C double bond O at the 1 and the 4 position. And then I join that to my amine, losing 1 hydrogen. Again, we're in the 1 and the 4 position, which is opposite each other. And we have a trailing bond where we've lost the hydrogen, put our pi bond in, don't forget that pi bond, that ring. And here is our amide bond between the C double bond O and the NH. And again, the trailing bonds would also be amide bonds. So what do we use Kevlar for? Well, the obvious one that most people know is bulletproof clothing. It's also used for fire-resistant materials, and quite often used in things like crash helmets. It's very strong. Sometimes tennis rackets in the frame have some Kevlar. So the reason it's used is for its strength, and that's a result of its structure. And what you have to understand about this, and this will be easy to understand when you've covered the aromatics chemistry pack, which is about benzene, but because in the benzene ring every carbon is only joined to 3 other things, every carbon is trigonal planar, flat. So the whole of Kevlar is a huge flat structure. Okay, so we say that Kevlar chains are flat or planar, if you want the chemical term or the scientific term for flat, and can pack very close together. So imagine the Kevlar chain being like a piece of paper. It's very flat. Imagine if you've got 500 sheets of paper, then they pack together very, very closely. Which means that when they're packing together very, very closely, because they're flat, the intermolecular forces, because polymers are just simple molecules, very big simple molecules, but they're not macromolecules, they're not endlessly repeating, they are simple molecules with intermolecular forces. They're going to be stronger than in other polymers because they've just got more points of contact. They're flatter, so there's more points of contact. The strongest intermolecular forces present in Kevlar, if you have a look back up at the structure, you can see that you have got a hydrogen bonded to an N. And if you remember from intermolecular forces that if hydrogen is bonded to N, O or F, then we are going to form hydrogen bonds between the molecules. And they're going to form between the nitrogen of one amide link and the hydrogen of another. So you could imagine drawing, like you've got your whole polymer structure, you've got an N and an H, and then you could imagine having another one, like an N and a H. Remember that hydrogen bond has to form between a delta plus hydrogen, which to be delta plus it has to be connected to a more electronegative element, in this case nitrogen, and it forms between the delta plus hydrogen and the lone pair on an N, O or F. Now because it can form between a lone pair on an N, O or F, then technically it could form in another way as well. So you could have the nitrogen with its hydrogen forming a hydrogen bond to a lone pair on an oxygen. Now that's not as common a thing to see because it's not where the hydrogen bond originated from the double bond O. This couldn't normally form a hydrogen bond, but this can form a hydrogen bond, the NH, and then it could form it to the lone pair, because that's what hydrogen bond is, delta plus H to a lone pair on an N, O or F. Right, so we've got these possibilities. So if we turn over, we can have a look at a couple of questions. So pause the video, see if you can attempt this question to give you some clues. We do have here 1,6-diaminohexane. So one of our monomers is 6 and the other one is dec, which is 10 decane dioic acid. So pause the video, see if you can draw them out. There you go. So to get to 6 in a hexane, what I've had to do is put 6 CH2s in the middle of my two ends. But to get to 10 in my carboxylic acid, because there's already two C's, I only put 8 CH2s in the middle. They're my two monomers. So now that you've got your two monomers, see if you can put them together to draw the repeating unit of the polymer. So you may have drawn something like that. I've chosen there to draw the carboxylic acid first, so I can see that I've formed my amide link here, my amide bond here, and the diamine second. But you may have drawn this slightly differently, so I'm just going to draw it out as if I've drawn the amine first. It's still correct. Both of these answers are correct. There you go. I've just drawn it out the other way around. Both of them are correct. Now we're going the other way around. Here we've been given the polymer, so what we need to do is locate the amide bonds. So there's always one between the C double bond O and the N, and each of the trailing bonds is also an amide bond. So we've got our two little sections. Pause the video, have a go, see if you can draw the monomers. There you go. So I've drawn them out. Remember that we'll put the OH back on the Q groups and the H back on the amines. You do need to draw the hydrogens out on N's and O's. It's only hydrogens on carbons that aren't shown in skeletal formula. We'll turn the page and have a look at the next one. Okay, so just like with our polyesters, you could form them from a single monomer if it contains both an amine group and a carboxylic acid in the same molecule. Then we can form our amide bonds at the ends rather than in the middle, so just the trailing bonds. Got amide bonds here and here. You can draw them straight out at right angles, like across the horizontal if you like. They've just been drawn out with some indication of some shape there. Doesn't matter that they're going down. So nylon 6, it says it's made from 6-aminohexanoic acid. See if you can draw that. Now again, to save time, I've drawn the CH2s in brackets, but notice this time it's not 4, even though it's hex, or 6, even though it's hex. It's 5 because there's 1 carbon in the Cu group and we need 6 carbons altogether. And so we end up with 5 in the bracket. What we're going to do now is we're going to remove the OH from the Q and the H from an N and draw our polymer. Remember that the trailing bonds show, the amide bonds show as linking to the next part of the polymer chain. And we've got amide bonds at both ends. Okay, so that's the end of the little section on polyamides, and in the next